Hey guys, let's do some physics. The first one's going to be kind of quick and easy. It's going to be letter B because I have two equal and opposite waves. So the first wave is a down and up, and when it completely overlaps with an up and down wave, they destructively cancel out, making a flat line. The next one, I have three pulses there. Right there, I drew as one full wavelength. Oh, that's by 1 meter. I know that because there's 1.5 meters here, and I have 1.5 waves. So wavelength is a meter. Now, I also know the frequency is 60. Oh, I can find the velocity then. It's f lambda. So it's going to be 60 times 1, which is going to be 60 meters per second. All right, let's flip this thing over. Now, a student wants to determine the speed of sound at elevation of 1 mile. So the first thing I know about the speed of sound is that sound depends on the material, aka the medium it's traveling in. And in this case, it's traveling through air. And when it comes to air, the difference of a speed of sound is based on the temperature. So the student got different results, trying to figure out why. Obviously because of the temperature. Wait, Jock, why isn't it from the longer tube? Well, let's see why. If I draw a tube here, the wave inside, the velocity doesn't affect that wave, it's the wavelength. Same with the wider range of sound and everything else. Those would affect the waves produced, but they wouldn't affect the speed of that wave. Now, I have a pipe closed at one end. The one end that's closed needs a node. The open end always needs an antinode to make a note and resonate. If there's not a node to antinode there, it won't work. So I have a frequency, and the length is 22. Since it doesn't resonate for any smaller pipes, that means that the first thing it's going to do is going to be its first harmonic. So looking at this, I know it's the first harmonic. That means I have a node and an antinode and nothing else in between. So I draw a normal wave. There's a node to an antinode. That's to be the first harmonic. And that distance is not a full wave. In fact, it's 1/4 of a wave. So this thing resonated with 1/4 of a wave. So the wavelength and made it is 88. Now, what are other lengths that will do it? Okay. I still need a node antinode. So now what I'm going to do is I'm looking at the next pair of node antinodes. So starting for the same node, the next note would be another antinode away. And that would be 3/4 of a wave. So that would be the next note it makes. And then, for the next one, it would be another antinode away, which would be 5/4 of a wave. The next one would be 7/4 of a wave. See how it kind of goes up every time. So those are the wavelengths that would make the next ones. So those are the lengths that would be making up. And you could solve for lambda in those cases, and that would be the length of the wave you want. I didn't do it because I just knew it would be 3/4, 5/4, 7/4. Again, the reason why is because I'm going to go from a node to antinode. Now, let's say it's open at both ends. Well, it's going to be an antinode that makes it resonate, not a node antinode. So if I draw my wave from antinode to antinode, that's no longer 1/4 of a wave. That's going to be half a wave. So now it won't resonate like it did before because it would have 1/4 of a wave. It needs a half wave. It's open. So it's going to resonate at half a wave, 1.5 waves, instead of 3/4, 5/4, 7/4. And finally, the closed pipe associated with helium. How would you discover what the speed of sound is? Well, I need to hit a fork, and I want to make sure it resonates. So I'm going to use a bunch of different forks. So I hit my fork, see if it resonates. If not, toss it aside, try it again, and go through maybe 50 forks until finally it happens. Once it resonates for the first time, I'm going to say, oh, that's my harmonic. I'm going to figure out the frequency because it's on the tuning fork. I'm going to get the wavelength because if it's a closed tube, and I made a mistake right here, you're about to see it, the tube is going to be a harmonic. So I said, oh, the first harmonic, get half a wave on it. But then I realized, oh wait, that would be for an open tube. Closed tube would be 1/4 of a wavelength. So I would solve for the wavelength and then solve for the velocity. Last but not least, we did this in class, let's make sure. You play a speaker, you have two tubes, and then they make notes at different lengths until it gets short. So since it's open and closed, I want a node, antinode end. So let's say I play that long wave you see right there. That's how long the tube should be to make that one resonate. Now, if the next node antinode pair, it had to be that long. You can see how huge of a difference it is between those lengths of the two tubes. It would be from a 4 to 3/4. It would be half a wave. Looking up there, it's not much difference there. So that can't be half a wave for a really long wave. That'd only be half a wave for a really short wave, which is why short frequencies would actually get these things to vibrate. So in summary, the reason why they don't vibrate together at first